Try looking at number 1 here on homework, 5.5. So it asks us to analyze and sketch the graph of the function. Label any intercepts, relative extrema, asymptotes, points of inflection. So, did you guys start off taking the derivative? Okay. Now, in order to start off taking the derivative of x is 1 minus 4 square root of x. Remember, that is what? 4x to the 1/2. So when I do the derivative there, 1/2 times 4, 2x to the negative 1/2 when you subtract 1. Okay. If we're going to set that equal to 0, to find critical values, 1 minus, now, what do we know about x to the negative 1/2? It's a square root of x in the denominator, yes? Or x to the 1/2 in the denominator. So it's going to be 2 over square root of x equal to 0. Okay? Now, right there, well, I'll go one more step. Let's go ahead and, if we're working to solve for x here, get the 1 on the other side. Or actually, how about if I move the 2 over square root of x the other side so it's positive? Or how about this? I'm going to write it as 2 over square root of x equals positive 1. I moved it over, but kind of flipped my sides. Now, one thing we know right now. Where is x? So what do we know? X cannot equal what in the denominator? 0. Right there, that's going to be a critical value. Okay? Because it's any place the numerator, or any place the derivative equals 0, right? But right there, before we even continue solving, I've got an issue, right? So that's where your 0 comes from, is that we have an x in the denominator right there. Now, if we keep solving this, I'm going to multiply the square root of x over, if you will. Square root of x times 1 is square root of x. So square root of x is 2. How do we solve? You're going to square both sides. So then we end up with x equals 4. So there is another critical value, yes? So right there, that's the magic that she did of just, sounds like she just said there's critical values 0 and 4.
Anytime you have a fraction, you need to set the denominator equal to 0.
Yeah.
And then set the whole thing equal as well if the x is
Yeah, if the x is in the denominator, you've got to pay attention to that, and that's where that came from. Officially, we set this equation equal to 0. It's just that here's the deal. I'm getting ready to multiply that, at this point right here, I'm getting ready to multiply that x out of the denominator. And so when I multiply it out of that denominator, if I don't notice it right here, it doesn't reappear later. Okay? So, now, if we think in terms of, I don't know, did you do a sign chart here? If we think in terms of, what do we say, 0 and 4, what is my graph doing? And I would maybe plug it into right there to decide. Is that a good place to plug it in? Okay. Now, what about number less than 0?
negative,
And I can't do the square root of a negative, can I? Okay, so that's going to be it doesn't exist over there. Okay, it doesn't exist over there. Which what we're saying then is my graph's not going to exist over there. It's what's ended up happening. Okay, what about between 0 and 4?
Yeah.
1 minus 2 over, say, square root of 1. Okay, there you go. 2 over square root of 1 is 2. 1 minus 2, that is going to be negative there. Yes? Okay. Then we plug in something bigger than 4. That's going to be 1 minus, say, 2 over square root of 9.
Yeah.
Because that's 2/3. 1 minus 2/3 is positive. Are you guys with me there?
Yes.
Now, what does that say about my graph?
Decreasing.
Yeah, it says that my graph is going to be decreasing between 0 and 4 and increasing to the right of 4. And that means 4 is going to become a min. Okay? I guess in my notes, I went ahead and found the value of that min. The fact that there's going to be a min at 4 comma something. Now, where are you putting that 4 into?
The original.
Now you're going into the original because it's a point on the graph. So square root of 4 is 2 times 4 is 8. 4 minus 8 is going to be -4. So I have a min at 4, -4. I'll be honest, I probably would have normally found that on my own later, but okay. Now, something that maybe I should have mentioned beforehand, I didn't. Over here to the left of 0, we said that that derivative does not exist, yes? Okay, let's go back to the original problem for a moment. What do you know about the original problem here? There's an x under the square root. What's that tell me for any x values in this problem? They all need to be positive, yes? So right there, we could have, I didn't think about that from the beginning, but right there, that tells me that in this graph, this is talking about the domain here, but my graph does not exist to the left of 0. So it doesn't exist to the left of the y-axis. Does that make sense? And I know that's not something that came up necessarily in the notes, but that's, you know, putting all of our graphing knowledge together is what it is. Okay? And that kind of makes sense then why this doesn't exist. We don't have to worry about anything to the left of 0. Okay. With that in mind, that means 0, we talked about 0 being a critical value, so if it's decreasing from here and then increasing over here, if the graph doesn't exist over here, what's 0 going to end up being? It's going to end up being a max, isn't it? I mean, it's an endpoint, but it's going to end up being a max because it decreases from 0 to 4. So for unusual reasons, that is going to end up being a max. So we are going to have a max at 0, comma, zero, because 0 minus 4 times square root of 0, so 0 minus 0 is 0. Okay, let's get over to second derivative. Did you find the second derivative?
Yes.
Okay, second derivative. Derivative of 1 is 0. Derivative of -2 x to the -1/2 is going to be -2 times -1/2, so 1x to the -3/2, right? Which x to the -3/2 is what? 1 over x to the 3/2. And if we set it equal to 0, you can't really set it equal to 0, can you? You can't set it equal to 0, but again, where does the denominator, or where does this second derivative not exist? Where does it equal 0? Well, it's never going to equal 0, but where does it not exist? This is again back to x cannot equal 0, which 0 we've already established is the left side of the graph, right? So really, when we go to talk about concavity, my graph goes from 0, we don't have any other critical values, so there's going to be all one concavity is what it's saying. There's not going to be a change in concavity. So if I plug in any number to the right of 0, so any positive number. 1 divided by 1 to the 3 halves. It's going to be positive. Okay, so if this is my second derivative, then that means my original graph is going to be concave up. Okay. Now, trying to think, what else do we have? Anything else? Yeah. I guess she did talk about labeling any intercepts. We already know there's an intercept at 0, right? 0, 0. Yeah, and mine, did she show find the intercepts in her notes? No? Okay. Okay. Reminder, okay, when do y-intercepts occur? Y-intercepts occur when x is 0, right? So just as a reminder here. So y-intercepts occur when x is 0. Well, if you go back and put in 0 to the original problem, 0 minus 0, and there we're going to, didn't we already talk about that point 0, 0? X-intercepts happen when y equals 0. Well, y equals 0 is putting the original problem equal to 0, so x minus 4 square root of x equal to 0. I have one thought. Yeah. Yeah. I kind of did a creative thing here, if you want to call it, where I factored out a GCF, not typical, of square root of x. Now, think about this. Okay, so if I factor out square root of x, from x, if you divide by a square root of x, what are you left with?
X.
Square root of x? Because what? Okay, think with me. Square root of x times square root of x is what?
X.
X minus the 4 equals 0. And what you can do here, as I said, it's not typical, but you can set each piece equal to 0, right? And so you have square root of x equals 0, which is just going to be x equals 0, and square root of x minus 4 equals 0, which, what? Square root of x equals 4. Go the other way.
Plus or minus 2.
No.
Square root.
How do you get rid of a square root?
Oh, 16, we're doing
16. So right there, there was y-intercepts. You have x-intercepts of 0, 0, we already knew, and 16, 0, which I didn't even end up putting that on mine. Okay. Lots of information, I know. Let me scoot this over. I know you guys have already seen the graph. I don't know if you have it sitting there in front of you or not, but I mean, officially, I don't know, there's my 16, if you will. Okay. Other key points, what did I have to know? 4. Okay. So again, this is a unique graph. Critical values of, there's 0, x-intercept of 0, right? There's an x-intercept of 16. Min at 4, negative 4. I didn't label that down, sorry. And then what's my graph doing? It's decreasing, increasing, and concave up. So, well, I kind of missed my... And keep in mind, you can't see it, but it does keep going through there. Okay? At least as it's shown there. So, anyways, it's a different problem. I get it. I get that it's difficult. I'm not going to argue that. Not going to argue any of these. Okay? Let's pick something else to look at.
6. Also 11.
Yeah, 6. Specifically on 6, the double derivative. I agree.
Yeah.
Okay?
Because like, yeah.
Let's look at 6. Wait, we have what? A, B, C. Never mind. I'm going to use just the plain graph. I decide I want a graph. Sorry, it's bright. Okay, so what do I need? I need the original in here, don't I? And the original we have, it goes up. Sorry, I have to see it pass behind my other two graphs. Okay. Something like that?
Yeah.
We're going to pretend we have A, we have B, and we have C. Is that all we have?
Yeah.
Yes, I saw the X down there and thought that was something else too. Now, and on this one, what does it tell me? This is the derivative, yes?
Yeah.
That's what we're provided. So use the graph of the derivative to sketch the graph of f and the graph of f prime. Okay, so where to begin, where to begin? Which one do you guys want to do first? F first?
Yes.
Well, and I guess either way, what I'm going to do is I'm going to set up a sign chart down here. And I don't know what she had showing. Did she have anything showing?
Yeah. Wait. I don't think so. I think
Okay.
it was just literally. I wrote stuff down, but I don't remember if she had that.
Okay. Well, what I'm doing here, my brain works best with sign charts so I can get everything organized. Okay? So I have the information. I don't have to process it. So I'm going to set up a sign chart. Key points on my sign chart are going to be A, B, C, yes. And I'm purposely just kind of lining it up there. Now, what do we know about the derivative graph? We know that to the left of A, it is negative. Because this is a derivative graph, right? In between A and B, it is positive. In between B and C, it is negative. And to the right of C, it is positive. So that's what I know just by glancing, right? Now, with that in mind, this is the derivative graph. And so I guess I'm going to probably kind of end up leading us towards, well, what does a negative derivative tell you in the original graph? It's going to be decreasing, yes? So I guess we're going to decrease to the left of A, increase between A and B, decrease between B and C, and increase to the right of C. Does that make sense? I'm pairing up the fact that my derivative was negative or positive. That tells me my original function f is increasing or decreasing. What does that tell me about A, B, and C on f? A is going to be a min on f because decreasing, increasing. B is going to be a max, and C is going to be a min because of my changing between increasings and decreasings, right? Okay. Now, I'm trying to think, do we have enough information? I'm almost ready to graph my original graph. There's one other thing we could talk about.
Concave up and down.
Well, if we go to let's talk about in reference to the second derivative for a moment. I guess I'm going to kind of end up doing another sign chart here, right below it. Okay. Because this is the derivative graph, yes?
Yeah.
Go back. Remember the chart I referred to yesterday, where it was F prime, F double prime, yes? And we talked about that, for instance, trying to get this piece right here. We have that information there, yes? Huh?
I thought F double prime represented concavity.
It does. Is the chart set up the other way? I thought it was set up that way. I could never. In my brain, it all works out. Yeah. Okay, but it does, because what it's saying here is the positive second derivative represents the original concave up. Negative makes it concave down. Now, the reason I put this in here is because I want to talk about this row right here. Okay? An increasing first derivative makes the original concave up, and it makes the second derivative positive. Are you seeing where I'm going with this? So what's my graph doing? It starts off increasing up to where? Not A. Whatever that point is there. We don't have a number for that point, do we? But it's that point in between A and B. And so what's happening here is that is increasing. Increasing means my second derivative would be positive, yes? And then my graph itself is going to be concave up. Okay? What happens after that max? My graph starts decreasing to that min there, yes? And so that whole time that graph is decreasing, so what's my original going to be? It's going to be concave down. And then to the right, my graph is increasing. It's going to be concave up. Now, those red tick marks I make, what are those going to be on my original graph? Those are POIs, points of inflections, because concavity changes, yes? Okay. Okay. My suggestion, I don't know. I was going to draw the original graph first. I don't know which one's better to draw first. But we've got all the information for the original graph, okay? And so this is my derivative, the original graph. Because my derivative starts off negative, what's this start off doing? It's going to be decreasing. Okay? At A, there's going to be a min. We don't have heights here. Okay, so this whole graph as I draw it can be shifted up or down vertically. Okay, we don't have the y values. That's just not something you usually have. So to the left of A, my graph is decreasing. We're going to decrease, and then I'm going to have a min under A. Now, does this make sense with what we're doing here? We're decreasing and we're what? Concave up. Am I doing that? It's kind of natural, but I am, right? Then a min under A, then what? We're going to be increasing.
Through the inflection point.
Okay, we're going to be increasing. And through the inflection point over to B. Now, the idea here is,
Yeah, right there. Perfect.
did I kind of get an inflection point there?
Yeah, you did. Yeah.
Ish, we're ballparking it here. Okay, so there is a POI, there is a min, here is a max. Now what?
Same thing. To your question.
We're decreasing to a min under, ooh, I almost missed, I don't know. We're going to pretend there's a POI there. It's not bad, I guess. And then there's a min down here. And then we are back to increasing. Okay? Now, this was f of x, which I know. We did all this, and the whole issue was second derivative, right? But on the flip side, I also feel like you guys aren't going to complain. This is all a big struggle, I know. So, okay. Now, I will say, here's one thing that I noticed. As I look at this, my green that I just drew in here, f of x, notice it's like that W shape, which is like a 4th degree problem. Okay? What was the original black? Or, that's my original. The black was my first derivative, which is like a cubic, 3rd degree, yes? What's my second derivative going to look like? A parabola? Because think about it, like this would be, if this is my original, and I'm not saying it is, but it kind of looks like x to the 4th, right? And then the derivative here kind of looks like x to the 3rd. So my parabola is, or my second derivative is very possibly going to look like a parabola. Now, okay, guys, we're going to go use these pieces right here. Okay? That's what I know pretty much, is that my second derivative is positive, then negative, then positive. So I know to the left of my POI, are you with me? To the left of my POI, my graph is positive. In between my POIs, my graph is negative. To the right of my other one, so are you seeing where I'm going with this? Ooh. Something like that is my second derivative. It's a mess to see, isn't it?
So that's why on number 5, f of x is a 3, f prime of x is a 2, and that makes f double prime of x just alone.
Mm-hmm.
Okay.
I like that connection. I mean, you can't 100% use it because not all derivatives are basic polynomials like this. But I like it because I can see, oh, that looks like an x to the 4th, an x to the 3rd. So now I'm looking for an x to the 2nd. Notice it was positive, negative, positive. Notice I attempted to cross right there at those key points. Okay, because a 0 on the second derivative became a point of inflection. Okay. Yeah, we're already well into the second half of class. I know. No, we've been struggling. It's not a, hidden thing. As I said, I just want to do 1 through 5. I don't think I'm going to do 6 and 7 this next lesson, but 1 through 5 are not short problems. Optimization are not short problems. So, I don't know. I know we only hit 2 homework questions with all that, didn't we?
Yeah.
I can't explain them quickly. I'm sorry.
That's okay.
I don't think you want me to explain them quickly either, though. It's just a tough, it's tough right here.
For like the test, or are we gonna have time for 5 questions?
Well, not everything in this chapter has been
That's true.
long and dry. Not everything has. So, okay. I'm going to end my question video and then start my lesson video. So.